Okay, so let's talk about fluid force. Now here's the definition. This is the definition of the force F exerted by a fluid of constant weight density omega. And here down here we have a common weight density. This is the weight density for water. Water has a weight density of 62.4 pounds per cubic foot. So any application of the fluid force of water, we'll be using this value for omega. So anyway, the fluid force F exerted by a fluid of constant weight density omega against a submerged vertical plate region from y equals c to y equals d is given by this integral. F is equal to omega times the integral from c to d. That's the two y values, two horizontal lines. Hy, where Hy is the depth of the fluid at y, and Ly is the horizontal length of the region itself at y. So this integral will give us the fluid force, and we have that fluid force, that weight density here for water. So using this, let's go ahead and do an example. All right. This here, and this example, what we're going to do is we're going to find the fluid force exerted on the vertical side of a tank, and these dimensions are going to be given in feet, and the tank is going to be full of water. So what we're doing, we are going to find the fluid force. We're going to find the fluid force on the vertical side of a tank. All right. So let's go ahead and look at this, the side of this tank. So the side of this tank looks something like this. The side of the tank is a trapezoid, and the top of the trapezoid is 4 feet across. So 4 feet for the top of the trapezoid. That distance there is 4 feet. And the bottom of the trapezoid, the bottom base, is 2 feet. We have 2 feet at the bottom. And let's see, the height of this trapezoid is 3 feet. So the height here is 3 feet. All right, so what we want to do is we want to identify Hy and Ly, and because we know it's a tank of water, we know the value of omega is equal to 62.4, and that is in pounds per cubic foot. All right, so we have this picture, and what we want to do is we want to kind of use the symmetry of this thing a little bit. So I'm going to create an axis system where my x-axis is actually the very top. That's going to be my x-axis. And the y-axis is going to go through and bisect this trapezoid, so that there's 2 feet on this side, 2 feet on this side, 1 foot down here, 1 foot down there. So this is my y-axis. So that's my axis system. All right, now that I've attached an axis system, I can actually come up with some functions. Okay, well, the formula says what I want to do is I want to integrate from c to d omega times hy times ly dy, where hy is the depth of the region. Well, if we subdivide this region here, if we subdivide this trapezoid into little pieces, we subdivide it into little pieces. Well, the depth of each of those little pieces, or the hy we're talking about, is just going to be the opposite of the y value of a point at the center of that representative rectangle. So if you look at a point right at the center of that representative rectangle, that's just the y value of that point. The x value of that point is 0. The y value of that point is a negative number. So the depth hy is actually the opposite of the y value. It's the opposite of the y value for that point. All right, now ly is the length of that representative rectangle, or the length of the region, the horizontal length of the region, based on this representative rectangle. And you can see this region goes from here to here, which is from the left-hand side of this trapezoid to the right-hand side of the trapezoid. And what we have to do is we have to come up with a way of writing that as a function. Those would be linear functions. Each side of the trapezoid would be a linear function. This point here would be the point 2, 0. And this point here would be the point where x is equal to 1, because we're 1 to the right, because this is 2 feet. So we're 1 to the right. And the y value, well, we're 3 feet down, so the y value would be negative 3. So we have 2 points there. We can come up with the equation of a line there. We also have these 2 points. This point over here is negative 2, 0. And this point over here is negative 1, negative 3. We only need to come up with the equation for one line though, because once I find out how far it is from the x-axis or from the y-axis to that line, it's the same distance on the other side. So once I find an equation for that line's x value, for the x value of that line, I can just double that x value in order to get the total distance. So let's see. Let's come up with an equation for this line right here. Well, an equation for that line, since I have the 2 points, I can find the slope of the line. The slope of the line is going to be negative 3 minus 0 over 1 minus 2, which is negative 3 over negative 1, which is 3. That's the slope. And an equation for the line would be y minus y1 equals m, which is 3, times x minus, y minus y1, which is actually 0 in this case. Sorry. Y minus 0 is equal to 3 times x minus 2. And then solving this equation for x, because what I need is I need the x value of that point. I need the x value of that point. That would be that distance right there, would be the x value of that point. And let's see, the x value of that point, if I divide both sides by 3, I get y over 3 is equal to x minus 2. And I add 2 to both sides. So I get x is equal to y over 3 plus 2. So I have that equation. And because it's actually symmetric, the length of any interval, the length of the region at y is actually just going to be 2 times this x value, 2 times y over 3 plus 2, which is, what's this going to equal? This is going to be 2/3 y plus 4. So there I have everything I need, and I'm going to calculate the fluid force. Well, here's the formula for the fluid force. The fluid force is going to equal omega, which is 62.4, times the integral from c to d. Well, we're integrating with respect to y, so c to d is actually going to be from negative 3 to 0. from -3 to 0, because we want to integrate along this entire region from the bottom of the trapezoid to the top. Hy is negative y, and Ly is 2/3 y plus 4 dy. So this is going to give us the fluid force. So let's go ahead and do that calculation there. Well, let me see. That's going to equal here. We have negative 2/3 y squared. So it's going to be, we're going to have 62.4 times the integral from -3 to 0 of negative 2/3 y squared minus 4y dy. Okay, so this is equal to 62.4 times, and then when we integrate this, well, adding 1 there, we get, this will be -2/9 y cubed minus 2y squared from -3 to 0. Let's see what we get here. Well, when we plug in 0, everything wipes out. So all we get is 62.4 times -2/9 times y cubed, which is -3 cubed, minus 2 times y squared, which is -3 squared. All right. Well, this is negative 27 over 9. Negative 27 over 9 is what? -3? -3 times -2 is 6. And this is -2 times, or sorry, this would be 2 then, times 9, which is 18. And this whole thing is negative because it's the subtraction side, right? So we get that this is going to be equal to negative 62.4 times -12. Let's see what that yields. Negative 62.4 times -12 gives us 748.8. And let's see, what are we doing this in? We have everything here is in feet, and this is in pounds. So I believe this is foot pounds. Oops. Let's see, this is in pounds per cubic foot. Oh, this is in pounds. Yep, so that's 748.8 pounds. We're not calculating work, we're actually calculating the fluid force. So there you have it. That is the first example of fluid force.